The souls should stand ajar, ready to welcome the ecstatic experience. A very good evening to all. I extend my warmest welcome to all for the second day of the Faculty Development Program on Exploration of Mathematics in Emerging Fields. I request Dr. R. Praveena, Assistant Professor, Department of Mathematics, to welcome the gathering.
Warm good evening to everyone gathered here. Thank you to each and every one of you for being here with us at this 5-day International Virtual Faculty Development Program. The beginning is the most important part of success. With this note, I express my hearty welcome to our chief guest, Dr. P. Sam Johnson, Professor, Department of Mathematical and Computational Science, National Institute of Technology, Karnataka, for his beautiful occasion. Welcome, sir. It is my pleasure to welcome Dr. N. Muthumani ma'am, Principal, PPG College of Arts and Science, for this wonderful knowledge sharing session. Welcome you, ma'am. I am very happy to welcome Mr. V. Ratanakumar, Head Department of Mathematics. Welcome you, sir. I express my sincere welcome to the participants from various colleges and universities. Welcome you all. On behalf of our department and my own behalf, once again, I welcome you all.
Thank you, ma'am. Expand your horizons with each word learned. Fluency is the key to a global perspective. I request Mr. V. Ratanakumar, Assistant Professor and Head, to introduce our chief guest of today.
A happy and pleasant evening to one and all present here. I'm very glad to introduce our resource person, Dr. P. Sam Johnson, Professor, Department of Mathematical and Computational Sciences, National Institute of Technology, Karnataka, Surathkal, Mangalore. He has served as a teaching assistant at Alagappa University, Karaikudi, and as a lecturer at both SRM University, Chennai, and the SSN College of Engineering, Chennai. Following this, he currently serves as a professor at National Institute of Technology, Karnataka, Surathkal. He has received several professional recognition and fellowships, including a merit scholarship in MSc from 1998 to 2000, achieving the university second rank in MPhil the year 2001, qualifying for the national eligibility test in 2003, and being awarded a junior research fellowship from 2003 to 2005. He has published more than 40 research papers in national and international journals. He has completed 3 funded projects from NPHM and SCRB, and he currently possesses 3 ongoing projects. He has guided 5 students to successfully complete their PhDs and is currently supervising 4 more. He has organized several workshops and seminars sponsored by NPH. He has received a travel grant supported by the Department of Science and Technology, Government of India, to attend the International Congress of Mathematicians in Korea. He has served as a reviewer for a significant number of national and international journals. He is a life member of various professional bodies, including the Indian Mathematical Society, the Ramanujan Mathematical Society, the Malaysian Mathematical Sciences Society, etc. He has actively participated and presented numerous papers at conferences, attended 18 workshops, and delivered 26 invited talks in various institutions. With this short profile, I'm glad to welcome you, sir.
Thank you, sir. The invariable mark of wisdom is to see the miraculous in the common. May I request Dr. P. Sam Johnson, Professor, Department of Mathematical and Computational Sciences, National Institute of Technology, Karnataka, Surathkal, Mangalore, to take over the session.
today I would like to tell some applications of linear algebra. So I hope you know the concept of linear algebra. It has a variety of applications. It has a very core mathematics as well. And then if somebody is working on linear algebra, so then really a person can find lots of applications in various fields. So today I'm going to discuss some applications of linear algebra. In our life, so suppose if I take any object, whatever object you imagine, so most of the objects are symmetric. So therefore, I just want to correlate the presence of symmetriness, which is same as the presence of linear algebra in every field. So the objects which are not symmetry, very rare. Therefore, if somebody is working on any applications, basically, if any mathematical model one can convert into some equations, that equations can be considered as there are two types. So it's linear and non-linear. So linear and non-linear. So for linear, there are again two types. So if we have a domain and codomain or finite dimensional spaces, then we can think about metrics. So otherwise, if the linear map between two infinite dimensional spaces, we can call as an operator. So most of the non-linear problem, we try to solve with the help of linearity. So we will try to approximate that non-linear problem into a linear problem, because so many tools are available in linearity structure, so that certain things can be discussed easily. So now let me tell a simple example. Suppose I consider a matrix A is equal to B. So I have a map A. The matrix is of size m by n. Therefore, you can, for simplicity, you can think about it's a map between an n-dimensional to m-dimensional. Therefore, this map we would like to, this matrix equation we would like to solve. The order of the matrix is m by n. So if I give an input x, so we have an output which is ax. So here the problem is, most of the time, we need to solve an operator equation in which x is not known. So this x is not known. So we are given with a and b. A and b are given. So therefore, solving a matrix equation plays a very important role by understanding the structure of the map between the two linear spaces. There are several equivalent conditions on this. Suppose if I take a very simple case, A is a square matrix of order n by n. Then in order to say the system is solvable, if it is solvable, then we would like to know whether the solution is unique or many. And basically, we want to check whether the matrix inverse exists or not. So if the inverse of the matrix exists, then we have a solution which is nothing but x is x, which is nothing but A inverse B. But most of the times we may not have a square matrix. Then we may have a pure rectangular matrix which is of order m by n, and m and n are different. Then we cannot talk about the invertibility in the general sense. Even if it is a square matrix, that need not be invertible. Suppose a matrix is not invertible, then also we cannot discuss. So now I'm going to consider two cases. Number one, the matrix is a purely rectangle, and number two, a matrix is square, but it is singular in the sense non-invertible. Then we would like to identify some kind of inverse, so that we can come back, or we can find out some element x, which need not be a solution to the equation 1, but it has some association with the given b. So for a given B, we want to find out some X. So which matrix does this? So you know very well there is a inverse called Moore-Penrose inverse, which are denoted by A dagger, which is called Moore-Penrose inverse. So this Moore-Penrose inverse is very much useful even for a non-rectangular matrix because M and N are different. And then if a matrix which is not invertible, so Moore-Penrose inverse always exists. So what is Moore-Penrose inverse? So suppose A is a matrix of order M by N. So a matrix X of order N by M is said to be Moore-Penrose inverse or MP inverse. MP inverse. So if the following four equations are satisfied, so those equations are called Penrose equations. Those equations are called Penrose equations. So they are as follows. Number one, so Ax A is equal to A, and then 2x Ax is Ax, and the number 3 Ax whole star is equal to Ax, and the number 4 Xa whole star is Xa. So that the theory says that if for any A, this matrix always exists, which is unique, satisfying all the four conditions. So such X is called this symbol A dagger, which is called Moore-Penrose inverse of A. So what does this A Moore-Penrose inverse say? So we have a space here. We have a space here. A is a map. A is a map. So now I call this as a range of A. So range of A. So because when we have an equation Ax is equal to B, so if this system is solvable, what is the meaning? So if this system is solvable, which means that this B is in the range space of A. Because if B is here, then that vector can be written as a linear combination of the columns of A. Therefore, we have a solution X. But sometimes inside this range of A. So if suppose B is outside this set A, this is range of A, the B is outside. Therefore, this system is not solvable. The system is not. In that case, we want to know at least some solution which is near to this, so which is called least square solutions. So which means that we want to find out an element X in which Ax tilde is near to B. Ax tilde is near to B. What is Ax tilde in the range of A? So therefore, what I was telling, the Moore-Penrose inverse A dagger of B will give that solution, which is a least squares solutions, and then there could be many other least square solutions, among which, because X tilde is here, among which we can find one vector which is closest to the origin. Therefore, we can say we have a unique solution. So that is nothing but the least square solution of minimal now. Therefore, this kind of operators are playing very important role in applications. So both theoretical as well as computational aspect. If people who are working in computer science, so they can think about how many operations are used to calculate this Moore-Penrose inverse of A. So for example, if two matrices are there, A and B, then if A is a matrix of order n by n and B is also a matrix of order n by n, then we can find the number of operations required to find the matrix product. So normally we write in the big O notation. Therefore, people are trying to find out so whether the order is linear or quadratic or constant. So such calculations are there in those who are working in computational algebra, and there are several methods available to calculate the Moore-Penrose inverse of this. Because if A is a square matrix, or if A is a full row rank or full column rank, this A dagger can be found easily. There is a formula. There are many formula available. But if there is no such formula, so for general matrix, so there are theoretical work is going on. So therefore, if somebody is very good in computational, so they will be able to write codes. There are several open problems available in more Penrose Invest. Therefore, this is a kind of remark I would like to tell to the faculty who are working in computer science engineering, so that you can write code, you can write some algorithm. So let me give a simple example. Suppose if a matrix A is of order n by n, I want to find out its determinant. So if a matrix is of order 3 by 3 or even up to 4 by 4, we will be able to find its determinant. 4 by 4 is difficult, okay, no problem, but we will be able to find. But if somebody, if we are given with a matrix of order n, let us say n is 100, then how do we calculate its determinant of A? What is the procedure? How many operations are required? So therefore, it is not easy to go with the regular procedure. So that's what we use some other elimination method or row reduction method to find the determinant of a matrix. So, but in general, if you want to use a formula for calculating the determinant, it is very tedious. Therefore, people are trying to find out matrix. So what is an idea is, suppose A is a matrix of order n by n. So normally we take one row. This is called Laplacian expansion. Usually we take the first row. So then we consider the first element. Then we have a sub matrix of order n minus 1 by n minus 1. So now I have to find the determinant of this matrix. And then we have to multiply with this with respect to this constant. So therefore, in order to know the determinant of this n minus 1 by n minus 1 matrix, I have to apply the same procedure. Therefore, if somebody is writing an algorithm, so that algorithm is having the complexity level, which is order of n factorial. So it is too much. So suppose if somebody writes an algorithm, so which gives the less complexity. So therefore, it is more welcome. There are many other algorithms are available for matrix product A by B. There is a very standard algorithm which is called Strassen algorithm. So Strassen algorithm we can use in order to calculate the product of two matrices. So therefore, I would like to tell if because when in a computer, when we are giving input as A, so in a computer we are giving matrix as input. This is an input, but we would like to expect an output. So basically we want to know how many operations are required. So this is a matrix multiplication. We can write the terms entry wise. But there are many other methods which we will be able to write column wise. We will be able to write row wise. There are many methods. Therefore, this type of research is called computational linear algebra. There are two aspects. In order to write an algorithm with a less complexity. So suppose if I consider O of n square, the method 1, if I have an algorithm 1, which gives this complexity O of n, there is an algorithm 2, which gives this as a complexity. Therefore, we will use this algorithm. The reason is, suppose the size is doubled. Instead of having n, we have 2n. Then the operation, the complexity level remains same. So here the complexity level will increase. So therefore, if somebody is very good in writing codes using MATLAB, using Python, many other programming languages, so still there are many problems which are open in order to find some calculations. So this is the first point I would like to tell. Yes. So do you have any questions in this regard? So do you have any questions? Okay. So now we will move on to Next topic, the same continuation of this computer, the images. Suppose there is a sender, and sender sends some information, and then there is a receiver. So he sends some information through some media. So suppose I'm sending a text message to someone. Hello, how are you? So now the message, hello, how are you, will not go as alphabets. So because the machines may not understand, they can understand only the numbers. Therefore, you have a word. So how are you? How are you? There are three words with some symbols, the question mark. So therefore, it's a combination of collection of words. So therefore, I can call this as a word. This is a word. So this is a word. But in each word, there are alphabets. So there are three alphabets. So now what we are going to do is, so this word we can say has three numbers, but this three alphabets we would like to convert into numbers. Three alphabets we would like to convert into numbers. So in terms of the binary bits 0 and 1. So how you are assigning, there are many standard codes. For example, I can start alphabet A to 1. I can start B with 2. Then later on, I will convert this numbers, the natural numbers, into binary. So you know how to convert the natural numbers into binary. So it has only zeros and ones. Therefore, basically, we are converting into binary bits 0 and 1. And then we will be, I'm sending this information to you, to someone. Okay. Suppose the sender is sending this information. Suppose the receiver gets this information. How old are you? So the actual sender sends information, how are you? But the receiver gets a message, how old are you? So therefore, first of all, receiver has to know whether the message sent by the sender is right or not. Okay. Suppose if he comes to know quickly whether the information sent by the sender is wrong, and he can use some tool to correct it. So therefore, now for us, suppose if I received a message from my friend saying that how old are you, then definitely I would call him. So why have you sent this message to me? I would call. But here we are going to find a system. The system itself can identify an error. The system itself can correct the error. So therefore, not only identifying, it will be correcting. So now onwards, I will not be writing any alphabets. I will be writing numbers. I will be using the bits 0 and 1. So basically, we are going to predict the error. Then once we find some error is there, then we are going to correct it. So, but when big information sent, you will have a huge collections of binary bits 0 and 1. So in order to understand the basic concept, I will go with the simple binary bits, maybe a word of length 4, word of length 3, like that. So what is word? So word is a combination of bits which are zeros and ones. So now I consider a word of length 3. So 001 is a word. Then 110 is another word, etc. So remember, you can find an association with this word to a number, because this is power of 2 power 0, this is 2 power 1, this is 2 square. Therefore, this is a number for 1. This is a number for 2 plus 4, 6. Correct? Yes, 6. So 2 plus 2 square 4, it's 6. So now these numbers are not necessary now. Therefore, I will rub this. These numbers are not necessary. So now you can simply think about the numbers which are which are which are represented by zeros and ones. So for me, this is a word. So what is code? A code is a collection of words. Code is a set of words. So we are going to connect this word to an element and then we want to associate this with a matrix. Okay, so now for any word of length 3, it will be any word, okay, not a code. So now I will write here any word of length 3. It is of the form ABC. ABC belong to the set 0, 1. It can be A, BA can be A 0 or 1, B can be 0 or 1, C can be 0 or 1, everything. Therefore, these are the terms. So how do I represent this element? So now for a matrix, so we just convert into a column vector, which is ABC, ABC. So therefore, we would like to associate, we would like to tell what is ABC, because ABC is a column vector. Therefore, we are going to use a 3 by 3 matrix, which is an identity matrix 1 0 0 0 1 0 0 0 1 with respect to ABC. ABC. Therefore, this matrix is called a generator matrix. This matrix is called a generator matrix, which generates all words of length 3. So if I take A, B, C are 0, then it will generate a word of length 0, 0, 0. Therefore, this is a general. So this for us, this is a generator matrix. This is a generator matrix for a code. So in Hamming is a very scientist. Hamming is was a computer scientist. So he gave 7 by 4 matrix. 7 by 4 matrix. You have a 7 columns and 7 rows and 4 columns, which is a tall matrix. So this matrix he has used to find an error and then correct it. Now you have a question, what do you mean by error? Okay, so now, for example, I want to send a 3 length word. So this is a word of length 3. I would like to send to a receiver. I would like to send to a receiver. So what I will not be sending as it is. I will add a component to this and send. I will add a component to this and send. So what component can be added? So what I'll do is I will add the sum of all digits. So 0 plus 1 plus 1. So it is 2. 2 mod 2 is 0. Therefore, 0 is added. What is 0? It is 0 plus 1 plus 1 mod 2. Mod 2. That 0 is added here. That 0 is added. Therefore, instead of sending just 0, 1, 1, we will be sending the 4 digits 0, 1, 1, 0. Therefore, this last digit is called a parity check. So this is a single parity check. So we are adding 1 digit. Therefore, it is called single parity check. Single parity check. Single parity check digit. So therefore, suppose the receiver receives the information. Okay, suppose let me write the information what he receives as 1100. For example, I'm saying an example. So therefore, the receiver checks. So remember, in this, suppose the receiver receives this. In how many places the positions are changed? Actually, here it is different. Here it is different. Here it is same. Here it is same. In third position also different. Fourth one same. Therefore, it is in 2 places there is a change. Am I getting what are you getting what I am saying? So 0 is sent to 1. 1 remains same, but 1 is sent to 0. Last digit remains same. Therefore, this message has 2 errors. This message has 2 errors. If there are 2 errors, so now the receiver checks whether the last digit is correct or not. What is the last digit? 0, which is the sum of all previous. So we are not going to consider this case. So we will be considering the case in which only one error occurs. Only one error occurs. So now what is an error? So now the error I will rewrite like this. So 0 goes to 1. Therefore, only one error. The rest are same. 110. 110. So therefore, this is a message the receiver gets. But still there is a problem. So can anyone say whether the receiver finds it whether the message sent is correct or not? So can anyone say whether the receiver finds that the given message is wrong or right? Thank you. Fine. Okay. So now what the receiver can quickly identify there is a wrong, because the reason is when you add 1 plus 1 plus 1 mod 2, then the answer is 1, but the last it is not 1, it is 0. So therefore receiver finds that the given message is wrong. The given message is wrong. So remember, we are discussing the case in which there is exactly one error in the message. If there is only one error, what is the problem in the receiver side? He can identify and check whether the given information is right or not. Because we have discussed there is only one error. As there is only one error, so he can detect that there is an error, but he cannot correct it. He cannot correct it because this could have been 0, this could have been 0, this could have been 0. At least one of them is 0. Not all of them, because only one error, right? So therefore he can, because if he wants to correct it, how he corrects? Suppose he may correct like this: 0 1 1 0. Now the last digit is right, but this is an actual information. Suppose he may correct like this: 1 0 1 0. That is also possible, but this is not an actual information, it is wrong. So he may correct like 1 1 0 0. So therefore it satisfies the last condition, but this is also a wrong guess. Out of these three, so one is only correct, but he cannot correct it exactly. So we are going to discuss a method in which if there is a single parity check in the digit, we can identify the error, and then we ourselves can correct it. We don't need to ask the receiver. We don't need to ask the sender. So we ourselves can correct it. That's what we are going to discuss here. Therefore, this is called computer generating codes. It's an application of linear algebra in computer generating codes. Okay, so now what we are going to do is we will be using a matrix which is a 7 by 4 matrix. Which is a 7 by 4 matrix. This matrix is called Hamming 7 by 4 code. Hamming 7 by 4 code matrix. So now I take the matrix to be 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. The next 0 1 1 1 1 0 1 0 1 1 0 1. This is a matrix. So remember, we are not going to deal with the 3 by 3 matrix. So we are going to, actual information has 4 bits. The actual information has 4 bits. So let us take the bit, I'm giving an example. Let us take the bit to be 0, or maybe I'll take 1 1 0 1 0. Okay, suppose this is a actual information. So when this information is, what is the size of the matrix? It is 7 by 4. Now I can consider as a vector, which is 1 0 1 0. Therefore it is of size 4 by 1. Instead of this, I consider this matrix. So therefore when I do the product, I will get the another matrix. I will get another matrix, the product. So what is the product? So the product will be, it is easy, 1. So you can easily calculate, actually 1 into the first one, 0 into the second, 1 into the first column, right? 1 into the first column, 0 into the second column, 1 into the third column, 0 into the fourth column. That way we normally multiply, right? So we can write columns. Therefore, it is basically adding the first column and third column. So if I add the first and the third column, I'll get 1, 1, 1, 1, adding the first and third, because we have a weight here in the first position, we have a weight in the second position, which is 1. Therefore, if I add this 2 columns, 1 and 3, therefore 1 1 1 and 3. Okay, what is, I think this is 0. Yes, am I right? Yeah, 0. So this is Sorry, this is also 0. Sorry, this is 0, correct? 1, 0. This is 1, and then this is 0. This is 1, correct? 1, and then this is 0. This is 1. Am I right? Yes. Okay. Okay, this is a message. So now what we are going to do is the sender is adding 3 bits. Now the sender is adding 3 bits. What are these 3 bits? The last 3. Remember in the matrix, if you look at this, this is an identity matrix. This is an identity matrix of order 4. E1, E2, E3, E4. So the remaining 3 rows we have used 0, 1, 1. Therefore, we have added 0, 0, 1, 0, 1, 1, 0, 1. Therefore, sender is sending this information. Sender is sending this information. So when the sender is sending this information, under the assumption that there is only one error, we are going to discuss a method of linear algebra to find out an error, to find out whether the error is there or not, and then we are going to correct it. That's what we are going to do it. So that we need a little bit linear algebra. So in order to achieve this. So I just tell once again, actual message is this, actual. So we have added, this is called parity check digit. So it is a 3-digit parity check of 3 digits. So this is called parity check. This is added. So therefore we have a new element, new code. This code is sent to the receiver. Receiver receives it, assuming that there is only one error. So suppose instead of this, suppose the receiver receives this message. Okay, now I'll write it as it is. So I just change only the first position for simplicity. 0, 0, 1, 0, 1, 0, 1. This is a message the receiver receives. As I told you, this is a wrong. This is wrong. It should have been 1. So now the receiver identifies quickly there is an error and he himself can correct it. He himself can correct it. That is the procedure we are going to see. So therefore, this code is very much popular. Remember what I have said is very simple matrix. So when we are dealing with, for example, there are so many applications of linear algebra. For example, if you are giving some keyword, when you want to search something in Google, we are giving keywords. There are so many things appearing immediately in fraction of seconds. Many things are appearing. But if you look at how the entries are, the links are appearing, you may be wondering that the links are appearing the more relevant which are coming on the top. More people are viewing the page which are coming on the top. Therefore, this is an application of linear algebra, which is more technical. That's what I did not want to take up. So what I'm saying is the matrices, the matrices in which the computers deal, which is huge, enormous. But what we have taken is a very simple example of size 2 by 4, so that we want to identify and then correct it. Yes. Okay, now let us come back to the theory. We have a 7 by 4 matrix. Then let me take the entry to be x1, x2, x3, x4. There are 4. Then I can multiply the matrix. Matrix multiplication can be done. So, but if you look at the last 3 rows, so last 3 equations, we have this x4 plus x5 plus x6 plus x7 is 0. This is a term. This is a term. So parity check matrix corresponding to that we can write. Okay. So to say is, suppose this is an actual code. This is an actual code we have sent. This is an actual code we are sending. But if you look at the corresponding matrix multiplication, because of this last 3 rows, 1, 2, 3, and we multiply with respect to this, you have 3 equations. I have written only 1 equation. There are 2 more. There are 2 more equations. So this equation must satisfy the condition. So because we want to have a same message, Therefore, whenever this vector, whenever we want to have a same vector, right? We want to have a same vector. That same vector I call as by x1, x2, x3, x4. All 4 components are same. We have 3 more components, which is x5, x6, x7. Therefore, when I equate these equations, so therefore there are three equations with three unknowns, with four unknowns, because there are three terms on the left side and then one term on the other side. So now there is a little a result which says that in terms of it. So this vector is the correct solution. If this vector is the correct vector which was sent by the sender, then these three equations must be satisfied. So what are let me write the other three equations. X2 plus X3 plus X6 plus X7 is 0. And then X1 plus X3 plus X5 plus X7 is 0. So you may ask why we have X1, X2. This is an operator equation. We are multiplying by X1, X2, X3, X4. And we have X1, X2, X3 and X4 up to 7 on the right side. So what is minus 7 mod 2? We are bringing that entry to this left side, which is nothing but 1, which is equal to 1. Therefore, we are having a term X7, on this side with a plus sign. Similarly, we will be doing with other terms. Therefore, we have three equations. So what I am trying to simply say is, we will be checking whether these equations are satisfied or not. We will be seeing whether these equations are satisfied or not. So now there are so many positions, 1, 2, 3, 4. In one position there is wrong. So we are going to correct it. Now the question is, so can anyone tell quickly, suppose one of them is wrong. Suppose let us say X1 position is wrong. X1 position is wrong. Only X1 position is wrong. All other terms are correct. So in which equation, among these three equations, which equation will be wrong? Can anyone tell this? Can anyone tell? So when I solve this equation, basically this is nothing but the matrix what are the values for on the left side? What are the values on this left side? This left side, what are these values? Where is X1 appearing? Is X1 appearing in the first equation? No. Is X1 appearing in the second equation? No. Is X1 appearing in the third equation? Yes. X1 is appearing in the second equation. So remember, instead of actual value X1, that X1 is wrong. Suppose X1 is 1. So actual X1 is 1. So then here it is 0. Suppose actual is 0. Here it is 1. Therefore, there is a difference. Therefore, this equation is no longer true. Therefore, the last equation is not correct because all other terms are correct. Only X1 is wrong. Therefore, the last equation will be wrong. Therefore, when I calculate the corresponding, I will be getting a number 001 if X1 only transmitted wrongly. I write it as a line. If X1 transmitted wrongly, is X1 is transmitted wrongly or incorrectly, so then we have a vector 001. So therefore, what we will do is, I'll repeat once again. This is an information we have. This is the information we received. X1, X2, X3, X4. I will verify this all three equations. If all three equations are correct, what does it mean? If all three equations are correct, therefore there is no error. Therefore, that is the actual information. Suppose there is an error. There is only one error. Therefore, out of these three equations, one equation is wrong. Then how do you check which equation is wrong, which variable is incorrect? That because of these values. So now we have four terms, X1, X2, X3, X4. If X1 is transmitted wrongly, by looking at these values, we can tell. So then we will have this. Suppose somebody is getting this number 001, he can quickly identify X1 is transmitted wrongly. Therefore, a person can correct X1 here. So therefore, this becomes a correct information. Suppose x2 is transmitted wrongly, then we would have received, what would have received? So we would have received, remember, only x2 is here in the second equation. Then we would have received 0, 1, 0. Therefore, we will check these three equations. If you are getting 0, 1, 0, then our conclusion is x2 is wrong. x2 is wrongly transmitted. Therefore, we will be correcting x2 in the final result. So let us summarize what I am saying. So actual information x1, x2, x3, x4. This is a 4-bit code. This is a 4-bit code. Sorry, word, 4-bit word. So now we have added 3-bit codes. How are we adding? By finding the summation of some numbers over here, numbers over here, numbers over here. We have used the Hamming 7x4 code. 7x4 code. Now, receiver receives some information which has 7 bits. Receiver receives this. So this is now I'm calling as x1 prime, x2 prime, x3 prime, x4 prime, x5 prime, x6 prime, x7 prime. So remember, this code we can apply only when there is only one error. There is only one error. If more errors are there, we cannot find. Therefore, if the only one error, so now I'll substitute these values in these three equations. As I said, these three equations. So it depends on the value, either 1, 0, 0, 0, 1, 0, 0, 0, 1. So we can quickly identify where there is a wrong. Okay, so now x2 we discussed. x3, look at where is x3? x3 is appearing in two places. x3 is appearing in two places. Therefore, we would have got 0, 1, 1. Suppose have we got 0, 1, 1, then x3 is wrong. Then x3 prime is wrong. x3 prime is wrong. Then we will be correcting x3 prime to some other number. Therefore, what I'm trying to say is, so this kind of error, it is very much useful. Therefore, it is automated. So nobody is going to check. So there is if a well-written code is available, therefore computer can identify the error on its own, and then it can correct the error on its own. So therefore, nothing is required. But what I have the 7 Hamming code. Hamming code is a perfect example. Is an example of a which code error this is. How many places the error is there? This is the best single error. It is a single error correcting code. So it is very important. Single error correcting code. Now you can think about, suppose if you want to correct more number of errors, therefore you need to go with bigger matrices. So that can be achieved with the help of well-written programming. So this is the second note I'm concluding. So do you have any questions on this Hamming code? How much time do I have, sir?
Maximum 1 hour, sir.
Okay, now when should I stop?
Sir?
Now when should I stop, sir? What time should I stop?
Maybe 7:45, sir. If you want
Okay.
more time, you can take your own time, sir.
Okay, sir. Yes. Okay. Yeah, thank you, sir.
Oh.
Thank you. Yes. So next application, if you have any questions, you can ask me now or later also. Now we will move on to the next topic, which is called Markov chain. So assuming that we have a town, So there are three restaurants. One I can say North Indian restaurant. Other I can say is a Chinese restaurant. Other I can say Chinese restaurant. So I can say some South Indian restaurant. South Indian restaurant. So we have 3 restaurants in the town. So now the town has some population. So let me take the population to be say 3,000. 3,000 is the population of the town. Okay, now remember just for a calculation. So assuming that nobody is having food in their house, so they are going to these restaurants. So now you may know in many sports event, South Asian Games, Olympics, there will be a village. So they all will be accommodated there, and they can choose their own food. They can go to different messes, similar kind. So it is not a proper that our usual typical town. So it is that type of town. So now people are going to this one of these restaurants to have the food. So the total population is 300. So first day, some set of people, maybe I'll call us in the initially 1,500 are going to South Indian restaurant. So maybe another 1,500 are going to North Indian restaurant, and then around 500 are going to how much? 3,500. Okay, let me check. This is 1,000. So going to Chinese restaurant. So 3,000. Yes, total population is 3,000. So, but what happens after this is day one, and they have an option of changing the mess. There is an option of changing the mess. So that is also happening in many hostels. So in beginning they allow students to go to different messes. After sometimes they will fix the number because arbitrarily people are coming, they cannot prepare it. So this is day one. Day one, this is a number. In day two, so the day two number is depending on some other value. So now this initial value I can call as say x naught, x y naught, z naught. This is on first day. Maybe x1, y1, z1 on day one. In second day x2, I am just saying the population is not same, which is following some linear formula. So which means that 0.7 percentage of x1 and then 0.1 percentage of y1 and then 0.1%, point not percentage, 0.1 times of z1. So maybe I can say 7%. There is a change. So 7% of x1. So now the number is reduced, and then 1% from not 1%. Yes, 0.1. How much? Yes, in terms of percentage. Yes. No, it is 10%. Sorry, it is 10%. 7. So this percent of people are going. So maybe if you say in terms of fraction, beginning there were 1,000 people, but if you calculate this notation, if you calculate this formula, then 0.7 into 1,500. So you have a number. So 0.1 into y1. So therefore the number gets changed. So maybe I please check this number. So I'm just referring some notes. So therefore this is a number. So this is the number in day two in South Indian restaurant. Therefore we would like to have a pattern. Therefore we would like to have a matrix. The matrix has the values 0.7, 0.1, 0.1, 0.2, 0.8, 0.2, 0.1, 0.1, 0.7. So if you see the corresponding column, the column sum is 1. Column sum is 1. Column sum is 1. What do you mean by column sum? What is the meaning of the column sum? What does the column sum indicate? So the total population remains same. The total population remains same. Therefore, it is divided among these numbers. It is divided among these values. Therefore, a Markov chain is a matrix. A Markov matrix is a matrix in which all entries are non-negative, greater than or equal 0. If you find the column sum is 1. The column sum is 1. So that is understandable because the population remains same. Even though the number is varying among the restaurants, the total population remains same. Therefore, we have a column sum. If I take each column, the column sum is 1. The column sum is 1. So we have the initial value. The initial value is nothing but x1, y1, Z1. Now, assuming that the entire the people in the town follow some pattern. When they are going from one restaurant to other restaurant, they are using this method. They are using this formula. Therefore, if I want to know on the 100th day or 8th day, if I want to know the population of this on these three restaurants, therefore I have to know the population in the previous day, k minus 1, k minus 1, because remember this matrix is fixed. This matrix is fixed. For this particular matrix, this process is going on. So now the question is, for large value of Q, what is the population? Whether you have a movement of population among these restaurants or will remain same, or very small amount of people will be shifting the restaurants or changing the restaurants. So that is the question. So therefore, this vector one can think about as a vector Vk minus 1. This is a matrix A. This is Vk. Therefore, we have a matrix equation. If we want to know Vk, we can write A times Vk minus 1. So as this number is increasing, so as k tends to infinity or k is large, as k is very large, whether we have a same population or not. So what we would like to know is, as k tends to infinity, do we have any population, any number, say let us say V infinity, such that if I apply A, then I will get the same. I will get the same. So if that can happen or not, that's what we would like to understand. So if that is happening, then we can say the people are in the saturated level, so they don't want to change the messes. They don't want to change the restaurants, which will remain the same. So this, with the help of the eigenvalues and eigenvectors, we would like to identify or we would like to calculate this V infinity. We would like to calculate this V infinity. So this V infinity is called steady state vector. So when we have a steady state, whenever we are applying this, population will remain the same among all the restaurants. Not necessarily equal, okay? Don't get confused with whether the number will be equal or not. So not necessarily equal. So maybe before going into this, maybe I will let me trying to find out or tell the answer. So in this case, the population will be a number. Okay, no problem. So now there will be a number V infinity. So our ultimate aim is to find this steady state vector. Steady state vector. How do we do it? So we want to know the powers of A. We want to know the powers of A, because what is Vk plus 1 is A square Vk minus 1. A square Vk minus 1. Therefore, it goes on like this. It goes on like this. So therefore, we would like to identify this steady state vector. Suppose somebody is running, somebody wants to start a restaurant, therefore he has to have this calculation, how people, the trend, how people are moving from one restaurant to other restaurant. So that, but the one big question is, nobody knows this matrix. Nobody knows this matrix. So who can tell this matrix? So Markov matrix, nobody can tell. So this one can approximately find by knowing the data. If 100 days data is known, then probably you can guess the Markov matrix. So therefore, this is another application of a Markov matrix. So I'm not going to tell you that how we can calculate this, but with eigenvalues and eigenvector, one can calculate this steady state vector. So repeated, applying this repeated value. So we started with V1, apply A, we have A V1, then apply A square V1, etc. Finally, we have to reach the vector V infinity, which is a steady state vector. So why this is happening? Because there is another interesting result. If I take any eigenvalue of A, the Markov matrix A, and then we have an eigenspace corresponding to lambda equal 1. First, one can check that lambda equal to 1 is an eigenvalue, and then you have an eigenspace. So that eigenspace has a dimension 1. So the corresponding vector, which is the single vector of unit length, which is nothing but V infinity. That is the simplest way of telling this. I repeat once again, you have a Markov matrix, so therefore it is a square matrix. So theoretically, as we calculated, the column sum is 1 plus 1. Therefore, lambda equal to 1 is an eigenvalue. So the dimension of the eigenspace is 1. So that space is spanned by a steady state vector. So what is a steady state vector? There are so many vectors, so many non-zero vectors which can span this, but we can consider a vector of length 1. So that vector is nothing but a steady state vector. So therefore, this is an application of Markov chain. How we are proceeding? This is called a chain. This chain is called Markov chain. Markov chain. Yes. So this is another application of this. So I will like to tell you one more application. You know the famous Fibonacci sequence. What is Fibonacci sequence? So we have two numbers 1, 1. We have two numbers 1, 1. How to generate new numbers? How to generate new numbers? So by adding the previous two terms, 1 plus 1 is 2, and then 2 plus 1 3, 3 plus 2 5, 5 plus 3 8, etc. It goes on. So suppose somebody wants to know the 100th element. 100th element. In order to know 100th element, the person has to know 98, 9th and 98. In order to know 98, then he has to know 3, which means that he has to know all of them. Therefore, one can write like this: an is equal to an minus 1 plus an minus 2. A first element is 1, next element is 2, and n greater than or equal to 3. So this is called a recurrence relation. This is called a recurrence relation. So this relation can be written in terms of matrix. We can write in terms of an, and then maybe an plus 1 and an in terms of some matrix with respect to initial value. So therefore, ultimately, we will be finding the eigenvalues of this, and then we will use a diagonalization process and calculate the formula for an. So remember, whatever formula we are providing, that should be independent of the previous terms. Therefore, if somebody is good in eigenvalues and eigenspectrum, and then people know about this recurrence relation, so one can check easily the equation is nothing but this. So now what is an answer? an, which is nothing but 1 by root 5, 1 plus root 5 by 2 whole power n plus 1 minus 1 by root 5, 1 minus root 5 by 2 whole power n plus 1. So this is the formula. So look at this is a very special formula. All the integers are irrationals. All the integers are irrationals. But look at the values. All values are natural numbers. You substitute any value, any value. Suppose if I know 100, a 100 if I want, therefore I can substitute a 100, 100, 100. For directly we can get without knowing a 99, without a 98. This is a simple application of linear algebra. So maybe I would like to tell you last point. So this, sorry, I will not be able to tell in detail, but I will give a quick idea. So we have a Earth. So there are so many satellites launched. So there are so many satellites. So the satellite, sometimes the satellite is moving. Suppose if I want to get a data from one place, then the satellite must be fixed. But Earth is revolving itself, rotating itself, and then it is revolving around the sun. Therefore, the satellite should also rotate. The satellite should also rotate. Therefore, we need some kind of energy which must be activated along this satellite. And then there is another kind of satellite. The satellite is fixed, so it will observe the entire area. For example, one area it is fixed, so it will observe when the Earth is revolving, rotating. It will take the picture in different places because the Earth is also rotating. Therefore, depends on the situation of this requirement. So we can control the satellite. There is a system called controllability, linear control system. Linear control system. So basically, we would like to discuss about two kind of forces or directions. So this is called tangential thrust. This is called radial thrust. This is called radial thrust. Suppose if we want to push the satellite away from the origin, we have a radial thrust. Then if you want to push along these directions, then which is a tangential thrust. So therefore, there is a control system you can represent in terms of a matrix. which is called a linear control system matrix. We can check whether the system is controllable or not. We have a system. We will be telling in terms of a matrix A. So the matrix satisfies some rank condition. We can say the system is controllable. What I'm trying to say is, suppose the tangential one is not working. Okay, tangential work is not working, but the radial is working, which means that the satellite is here, but we cannot move because it is fixed. The radial is fixed. So even though if we miss a satellite, there is a hope that a satellite can be set right after some time because because it is missing this direction only. But whereas if the radial thrust is missing, then the satellite will be going this direction. The satellite will go away from the Earth, away from the Earth. So if this thrust is missed, if the system is not controllable, then we will not be able to control the satellite that will be going away from the Earth. So we cannot bring it back. We cannot bring it back easily. So therefore, these are all answered in terms of simple matrices by finding ranks and other type of matrices, the Gramian matrices and others, which has a little application oriented. So more application oriented. So those who are working in operator equations and observability matrix, so you can use this. Okay, so I with this I'll conclude my, maybe I'll summarize quickly. So what I have done it. So first I started with a system, whether the system is linear system is solvable or not. We discussed the inverse called Moore-Penrose inverse. So it has a lot of application, theoretical as well as computational. And then next we discussed kind of operations we require in order to do some matrix operations, matrix multiplications, determinant, finding eigenvalues, SVD, single value decomposition, so many things. So the number of operations required. So if somebody is good in writing codes, therefore you can write a good algorithm with a less complexity. So we discussed matrix multiplication, we require n factorial operations. So the complexity level is high. So maybe somebody can find out or work on to reduce the complexity level. So these are all related to computation linear algebra. So next we discussed some message we are sending from one place to other place in terms of words or codes. So is there any procedure to identify an error and then correct it? So we discussed a method called Hamming 7x4 code. In Hamming 7x4 code method is used in order to detect a single error, and then correct it. So therefore, Hamming 7x4 code is used. And then next we discuss the Markov chain. So you have a group of people, there is a distribution among them. That distribution is varying day by day. We want to know, is there any time in which the change of places from one restaurant to other restaurant, it's not huge. Whether can we reach that steady state? The steady state vector can be calculated with the help of linear algebra. So because the given matrix is a Markov matrix, so it has an eigenvalue, the eigenvalue is 1, and it has its eigenspace, the dimension is 1. Therefore, the vector of length 1 will be the steady state vector. So there is another application by finding the recurrence relation. Using the recurrence relation, can we find a formula to calculate the nth value directly without knowing the previous terms? Yes, by finding the eigenvalues and then diagonalization process, we can find the power of n. And basically, we will be finding power because the given matrix is diagonalizable. Using the power, we can write the formula for a power n using only n. No need to use the previous values. And then the last idea I was telling about the linear control system, in which the satellite can be controlled by considering the tangential thrust and radical thrust, which thrust can be controllable or not. One can check by finding some simple rank conditions, very simple rank conditions. With that rank conditions, one can find this. Okay, sir. So with this, I'll stop.
Dear participants, if there are any queries, you can raise your questions to our expert. Sir, there is a question in the chat box.
Okay.
Sir?
Okay, madam, I'll see that.
Okay, sir. Can you tell what will be Markov A matrix for Frobenius sequence?
Frobenius sequence. So
Yes, sir.
the Markov matrix, we discussed the Fibonacci sequence, the recurrence relation, but Markov matrix we discussed in different
Sorry,
context.
sir. Sorry, sir. My question was wrong actually. I want to know that what will be the matrix for this Fibonacci sequence. So, that part.
Okay, sir. Yes, yeah, you are right. Yes. So actually, it is a very simple equation. So now we have an is equal to an minus 1 plus an minus 2. Otherwise, maybe I will avoid minus 1 minus 2. Maybe I'll write with, okay, it's okay. Anything is fine. Yes. An minus 2. And then a1 is a1 and a2 are 1. So what I'll do is that the second equation, so I take the second equation as it is. What I'll write as, this is an. Second equation I'll write an minus 1. How do I write an minus 1? An minus 1 as, can you guess, sir? Can you guess?
An minus 2 plus an minus 3.
No. Second equation I'll write an minus 1 is equal to an minus 1 only. It is a simple, direct one equation.
Okay.
Is this fine, sir? Okay.
No, I could not get because the sequence should be the sum of the last two terms. So an minus 1 should be an minus 2 plus an minus 3.
The second equation I have added unnecessarily because they are same, right, sir? Left side and right side are same. Am I right?
Okay.
Okay. So now, So now I'll combine these two equations. I'll write it as an minus 1 is equal to the matrix 1, 1, 1, 0 into an minus 1, an minus 2. So if I look at this difference, so this is n minus 1, the next step is n. This is n minus 2, the next step is an minus 2, n minus 1. So therefore, what we want to know is, so basically, sir, this is a matrix. This is a matrix A. So I will explain once again. Suppose if I start with this is 1, A1, A2. What do I get on the right side?
A2, A3.
A2, A3. So therefore, this is A2. So now if I apply again A here, so I will get this is A3, A4. A3, A4. Therefore, for me, the matrix A is this. So this is a matrix. So the matrix A is, so for which I will be finding the eigenvalues. So here one can easily verify that whether this matrix is diagonalizable or not. So if I calculate the corresponding eigenvalues to this matrix, the eigenvalues are minus 2 and 1. Minus 2 and 1. Maybe one can check this. Yeah, minus 2 and 1. Okay, no problem. This is a matrix. So what we want to know is,
Eigenvalue are 1 and 0. No, I don't think so.
yes, sir. Eigenvalues of this matrix one can find. I think it is minus 2 and 1.
No, sum should be 1, right, sir?
Yeah. Yes, correct. Yes. Yeah, correct. No, yeah. Here, yes, sir. So here the eigenvalues, if we calculate, the eigenvalues are 1 plus minus root 5 by 2. So these are the eigenvalues. So there are two eigenvalues. That's what we have used in the last line. So if somebody has noticed, this is an eigenvalue. This is an eigenvalue. This is another eigenvalue. Another eigenvalue. So what we want to know is finally, this expressions are, if you calculate, we want to have a corresponding notations. If you look at it, this is nothing but the power. This is nothing but the power of n. Maybe I'll write in the one more steps. The matrix A is diagonalizable, then this matrix A can be written as P D P inverse. So therefore we need A power n. So A power n and be P D power n P inverse. So D is nothing but the lambda 1 and lambda 2. So lambda 1 is 1 plus root 5 by 2, lambda 2 1 minus root 5 by 2, P inverse. Therefore we want to write A power n. Therefore for that reason only, so we are getting power n plus 1. Power n plus 1 in the previous case. Therefore here the matrix is 1, 1, 0, 1. So whatever matrix I have written, this is a matrix. This is a matrix. We apply it. Yes.
Okay, sir. Thank you, sir.
Okay.
Thank you very much, sir.
Welcome, sir.
Hope there are no more questions, sir. Shall I continue, sir?
Yes, ma'am. Yes.
Thank you, sir, for the inspirational and proficient session. Many thanks for sharing your insights. Your input has been incredibly helpful. When you are grateful, fear disappears and abundance appears. I request Dr. A. Maheshwari, Assistant Professor, Department of Mathematics, to deliver the vote of thanks.
It is with great pleasure and gratitude to extend my heartfelt thanks to our esteemed chief guest, Dr. Sam Johnson, Professor, for accepting our invitation and for being here with us today. It was very unconventional and inspirational thoughts have truly inspired us. Thank you, sir. I express my sincere thanks our admired principal, Dr. Yan Muthumani ma'am, for her support and guidance. Thank you, ma'am. I would like to thank Mr. V. Ratna Kumar, Assistant Professor and Head, Department of Mathematics, for his constant support and encouragement. I express my sincere thanks to all the heads of the departments and staff members of PPG College of Arts and Science for their endless motivations. I extend my sincere thanks to our participants from various colleges for your active listening. Once again, I thank you all for your whole cooperation. Thank you all.
Thank you, ma'am. Dear participants, I request you to kindly fill the feedback form which is posted in the chat box. Thank you for all the support given to us today. You all can leave the meeting once you fill up the feedback form. Thank you all once again.